All right, so welcome to Squishy Circuits. Just next slide real quick, and then I'll pass it off. So my name is Charlie. I'm a 16th grader at UC Berkeley, studying math and physics. I'm really interested in really big things. So I study things like the whole universe and it's called cosmology. So that's sort of what I'm interested in. And I'm going to be sort of looking at the chat and sort of answering your questions as we go along. So at any point in the presentation, please feel free to just ask questions in the question and answer feature. Would love to sort of answer all the questions that you might have about circuits and electricity that we'll be seeing today. And without further ado, I'm going to pass it off to my two wonderful presenters today. So take it away.
Hi everyone, my name is Christian and I am a 14th grader studying astronomy and physics at Berkeley. So I'm really interested in a lot of different things in space, but what I like to do is I like to work in the northern lights. So I work with how they work and when they happen. So I do all kinds of cool stuff with lots of pretty colors. So it's always a fun time. And I'll be one of the panelists today. So with that, I'll pass it off to our next panelist.
Hi guys, I'm Aditi. I'm a 13th grader in UC Berkeley. I'm studying physics and maths, or I plan to. And I don't know what I want to specialize in just yet, but that can wait. So I'm one of the co-panelists with Christian today, and let's start off with our squishy circuits.
Awesome. Yes. So if you haven't guessed by now, today we're going to be talking about circuits. But before we do that, we have to talk a little bit about electricity. So electricity is a form of energy that kind of results from these things called charged particles. And you can kind of think of these charged particles as little go-karts that kind of go around a track. So each electron or each charged particle is a go-kart, and each particle then adds to the power, which then is what creates electricity. So with that, I'm going to show you guys our materials that we will be working with today for our demos.
My name's Charlie. I'm a third-year physics major at Cal, and today we're going to be doing an experiment called squishy circuits. So for squishy circuits, we're going to need four things. So the first thing we're going to need is Play-Doh. So Play-Doh is going to be how we let the electrons move around the circuit. The second thing we're going to need are batteries. So the batteries are where we're going to get all these electrons from. The third thing we're going to need are alligator clips, which basically just connect the batteries to the Play-Doh, which let the electrons move around in them. And the last thing we're going to need are tiny light bulbs called LEDs that are going to be how we know if the electrons are moving around or not.
All right. So circuits are basically ways for energies to flow. And specifically, as it says on the slide, circuits are closed loops through which electricity is intended to flow. Now, this is very important, so keep this in mind. Polarity means direction. So you'll hear this term a lot when you see it, in the following slides, and it's a good thing to keep in mind. Polarity means direction. And why don't you guys type something in the chat, anything that you can think of that is an example of a circuit in your life. So feel free to put in the chat and let's see what we get. Lights, yeah. Hot wire fencing, ooh, bathroom fan, nice, wow. Guys, you know what you're talking about, that's great, yeah. So in the slide, it says, how do you see when it's dark? So like our tube lights or the lights that we have at home to light up our houses, that's an example of a circuit. And like many of you have mentioned, yeah, light bulbs, electric fans, heater. Yeah, those are great examples, guys. Okay, so the next slide.
So the first thing we need to do is get our Play-Doh. So what I'm going to do is I'm going to take out the Play-Doh and I'm going to roll it into a snake shape. Okay? and I'm going to break that snake shape off into two chunks. So now I have two sort of snake shapes. The next thing I'm going to need is I'm going to take a battery, and I'm going to take my two alligator clips, and I'm going to connect one of the alligator clips to each end of the battery and put those ends into the Play-Doh. Just stick it right in. And then what I'm going to do is I'm going to take the LED and I'm going to put it in the Play-Doh. Wait a second. It didn't turn on. Well, the reason is because if you look, one of the ends of the LED is longer than the other. And that's because the LED acts as a one-way switch. So the D in LED stands for diode. And a diode is a thing that electricity can only flow through one way. So if I put in the diode the other way, it lights up just as we expect.
Great. So we saw with the diode that electricity only flows in one direction. So bringing back this idea of polarity, then we know that the diode was in the right polarity to have electricity flow through it. So the next thing we're going to be talking about is kind of two different types of materials, or two different categories of materials. One is called an insulator, and what it means is essentially it doesn't let electricity flow. And the next is called a conductor, and a conductor is something that lets electricity flow. So I want to ask you guys now, type in the chat, you guys can think of any examples of what a conductor or what an insulator might be. Oh, rubber, plastic. Yeah, those are all great examples. Glass. Yes, it's true. Muddy field or smooth road. Yes. Yeah, so you can kind of think of an insulator as like a muddy road. It's really, really hard to drive through. So the go-karts can't really get through it all that fast. So you can kind of think of insulators that way. Whereas conductors are kind of like roads that are completely clean and flat, and they allow you to go at your full speed. So now I want to ask you guys, what are some examples of conductors that you might be familiar with? Metal, wire, steel. Yeah, you guys got it. Perfect. So these are kind of some common examples of both conductors and insulators that we are kind of familiar with that might be lying around our house. So silver, gold, copper, steel, seawater. Usually metals are really, really good conductors. Insulators are things that usually aren't metal. So rubber, glass, oil, even diamond. And those are all things that don't allow electricity to flow. All right, so now we're going to look at an example of how conductors and insulators work in a circuit.
So Play-Doh is a conductor, meaning electrons like to move through Play-Doh. But something like rubber, the thing these rubber bands are made of, is an insulator, meaning electrons don't really like to move through the rubber. So what do you think is going to happen when I connect the battery to these rubber pieces?
So go ahead and type in the chat what you guys predict will happen. All right, yeah, good guesses. Nothing. All right, let's see. Oh, sorry, let's see what happens.
So Play-Doh is a conductor, meaning electrons like to move through Play-Doh. But something like rubber, the thing these rubber bands are made of, is an insulator, meaning electrons don't really like to move through the rubber. So what do you think is going to happen when I connect the battery to these rubber pieces? It doesn't light up. And to make sure that I'm not tricking you and just putting the light the wrong way, here it is the other way. It doesn't light up either way. That's because the electrons don't like to move through the rubber in the rubber band.
All right, so this is our first activity. And this is important. So for circuits, for electrons to flow around a circuit, they always need the circuit to be closed. So for example, if we consider a drawbridge, if the drawbridge is open, right, cars can't pass through it. And it's a similar thing with electrons. Electrons really can't flow if there's a break in the circuit. Whereas if the drawbridge is closed, then yeah, it's the same thing. So how does this relate to the go-kart picture? Do you guys have any idea? Put it in the chat and let's see what you guys come up with. Switch, yeah. And sometimes in the way nothing can get through. Yeah, correct. So if we have obstacles that don't really let the car pass through, then obviously there's a break in the go-kart's pathway, and the go-kart won't be able to get through. And it's the same thing, except here the break in a circuit can be caused by switches. So if you go to the next slide, we'll see an example of that.
So right now, the light is not turning on because there's a hole in the Play-Doh. So what do you think is going to happen when I take this Play-Doh and I mush these other two pieces together with it?
Yeah, great answers, guys. You got it. Yeah.
That's right, it turns on. Now what do you think is going to happen if I remove it again?
Exactly. And here's the idea of a switch. Bye-bye light. Yeah. Yeah.
That's right, it turns off again. That's because only when the Play-Doh is connected can the electrons go through the full circle of the battery circuit setup.
Great. So we've seen how having a full road is very important for go-karts on a track, in the same way that having a full loop of wire is very important for electrons to flow and electricity to flow. So now we're going to talk about two different kinds of circuits. The first circuit is called a series circuit. And basically what that means is that everything in the circuit is connected such that there's only one pathway for the road, for the electricity to follow. You can kind of think of it like a NASCAR race. There's only one way for the cars to go. There's one road versus something else that we call oh, sorry. Go ahead. I'll let DT explain this one actually.
Sure. Yeah, so the second type of circuits that we'll be looking at today are parallel circuits. So in these kind of circuits, we have multiple pathways through which the electrons can flow. And you can kind of think of it as like multiple lines kept beside each other. And so we have different pathways, and we'll see an example of that in the next slide, or a couple of slides later.
Okay, cool. So we talked a little bit about the different kinds of circuits, and now we're actually going to delve into the specifics. So what is a series circuit and what does it look like? So a series circuit, like we talked about, is kind of like a road that only has one way to go, right? So you can imagine in this picture here, it's sort of what the electricity will do is that it will go around and it will go through all these houses, make the full loop all the way around and come back, right? But one thing you might have noticed is that there are areas in this circuit where it can go around the houses, and this is often what happens when there's a power outage at your house. Is the electricity doesn't have to flow directly through your house, so it can go around. It can take shortcuts, and this is what we call shorting a circuit. Cool. So, can you guys think of maybe some? Well, actually, we'll move on to the next circuit and then maybe ask some more questions. So this is going to be just a quick video of what a series circuit looks like. So
So the first thing we're going to look at is something called series. which basically just means everything is lined up in a straight line. So now what I've done is I've put two light bulbs right next to each other. So what do you think is going to happen when I connect the battery again?
Great. Yeah, so go ahead and type your predictions in the chat. What happens when the two alligator clips are connected to the ends of the Play-Doh? It will work. Work. Take one. We'll both light up. Both light up. Yeah, you guys are getting it. Great. So you guys have a guess for maybe how bright the LEDs might be? Okay, I see less bright. It will be none, no, because it needs to be split up. The energy. Yeah, all right. So let's watch it and find out.
So the first thing we're going to look at is something called series, which basically just means everything is lined up in a straight line. So now what I've done is I've put two light bulbs right next to each other. So what do you think is going to happen when I connect the battery again? They both light up. But the question is, what if I add a third one? How do you think it's going to change?
I'm seeing less light. Okay. Less brightness. Less. All right. Yeah, great. So let's see what happens.
They're dimmer. Well, what if we add a fourth one?
You guys have a guess for maybe what happened with the fourth one? Way less. Yep. Okay. Yeah. So you guys are starting to catch on to the pattern here. Maybe no light at all. Yeah. Those are all great. None. Those are all fantastic answers. Let's see.
It's kind of hard to see, but if we turn the lights off, you can see that they actually are still lighting up. They're just very dim. So right now, they're still lighting up, right? But if I pick one of them up and turn it the other direction, what do you think is going to happen now?
It won't work. More dimmer. No. Won't work. Yeah, those are all great answers. So let's see how your guys' predictions stack up.
Only the one I didn't turn around lit up. The reason is because the electrons can still run through the circuit when the light's the wrong way. It's just the light will only turn on if you have it facing the correct direction. I'll show the other one does the same thing.
All right. Yeah, great. You guys got it. You guys picked up. So in a series circuit, when you add more light bulbs to the circuit, the dimness goes down or the brightness goes down. And that's because there's more energy that has to be split up between all of the different light bulbs. You guys got it.
All right. So to start off with parallel circuits, what do you think parallel means? I think I sort of gave this away and explained it already, but go ahead and put your answers in the chat anyway. Let's see what we get. What do you think parallel means? There's a hint on the slide, by the way. Okay, so I'll go ahead and explain it anyway, and then two lines that never meet, yeah? Yeah, in fact, that's really precise, yeah. So parallel A circuit where there are many roots. Yeah, although they never cross but go together, multiple pathways. Yeah. You all got, if one bulb not working, the others will work. Yeah, guys, yeah. Okay, so parallel circuits look sort of like the ladder on the screen, where you have multiple rungs and or multiple pathways, and then which sort of correspond to the rungs on the ladder over here. And then if we were in an actual circuit, we would have a circuit component like a bulb uh, situated in each of these rungs or each of the pathways. And so yeah, so like it says that each branch, there's a device placed on each branch, and then so the electrons have multiple pathways along which through which it can flow. So let's see an example in the next slide.
The next thing we're going to look at is something called parallel, which basically just means everything is connected to the same pieces. So I've connected these two lights in parallel. So what do you think is going to happen when I connect the battery? They're going to light up. Let's try adding another one to see what happens.
Okay, I think the answer was given off.
The next thing we're going to look at is something called parallel, which basically just means everything is connected to the same pieces. So I've connected these two lights in parallel. So what do you think is going to happen when I connect the battery? They're going to light up. Let's try adding another one to see what happens.
Okay, let's pause it here. And what do you guys think will happen? Put it on the chat. It will work, okay. And what do you guys think? How do you guys think the brightness will be affected? Will it be, yeah? Less brightness, work but dimmer, okay. Dimmer, all right, okay. Same brightness, ooh, now we have it, okay. We're having conflicting answers over here. Okay, so let's play the video and see what happens.
What do you think is going to happen now? Let's add one more. Notice how they're not getting dimmer like they did in series. So right now, again, they're both facing the correct direction. What do you think is going to happen when I pick this up, turn it around, and place it back down?
Work, okay. Work, not work, okay. Which one do you think will work and which one do you think doesn't work? Only the bottom one will work, okay. One works, no. Okay, so let's play it and find out.
Only the one that's still facing the right direction turns on. Should does the other one too.
Okay, just pause here for a second, Kristen. Now, this has got to do, the reason why when Charlie turned it and one worked and one didn't is because of the polarity. And because one was in the correct direction, and so one let the electrons flow through it, but the other didn't. And let's check out this fun parallel circuit that Charlie put together for us. Ooh.
The next thing we're going to look at is something called parallel. So what do you think is going to happen now?
Yeah, and just as a side note, the reason why the bulbs had the similar level of, or at least they were equally bright during when we had parallel circuits and not when we had the series circuit is because the electrons have an equal chance of going through each pathway. And so because the electrons are the ones that carry the energy, and so because we had an equal number of electrons going through each pathway in the parallel circuit, we had the same level of brightness for each bulb. Whereas for series circuits, because the electrons had only one path which they could flow through, they had to share their energy between each consecutive bulb. And so there was less energy transferred to the bulb, and so we had less brightness. All right, so yeah, okay, so now, since we have time, let's look at a complex circuit.
So now we're going to try combining them. So what do you think is going to happen when I put the battery parts right here and right here?
What do you guys think? Put it in the chat. Work, okay. All three? Only one? Okay, okay, let's find out. Oh, only one. Which ones will light up? Yeah. One. Which one? The ones on the... Okay, so the only one that's... Okay. Dim, maybe. Dimmer. Okay. Okay, let's find out. Let's find out.
They all light up. So what if we had another one in series? How bright do you think these ones are going to be?
Oh.
So now we're going to try combining them. So what do you think is going to happen when I put the battery parts right here and right here? They all light up. So what if we had another one in series? How bright do you think these ones are going to be? They're all dimmer. But now, what if instead of connecting it right here and right here, what if I connect it right here and right here? Which ones do you think are going to be lit up? How bright do you think they're going to be?
Okay, so what do you guys think? Is the one on 3 are gonna light up? Okay. Okay. So you guys are saying, do you guys think that the farthest to the right is not gonna light up? Very dim. Okay. Okay. Very dim as in very dim. Okay. Do you guys think it'll be dimmer compared to when we had all 4 connected? Or do you think it's gonna be brighter? Think back to the first time when we had only these 3 and before Charlie added the 4th bulb. Okay, 3 work, brighter, yes. Okay. Okay, and think back also to the concept we talked about, complete loops. Which one, I mean, keeping complete loops in mind, which one do you think will not light up and why? Dim, okay. Okay, okay, you know what, let's find out, let's find out.
They're just as bright as when I didn't even add this one, and this one's not lighting up. Can you explain why?
Not part of the loop, yeah, exactly. That's fantastic, guys, that's exactly it. Circuit not closed, yep, yep. Yeah, it wasn't part of the circuit, and so the electrons couldn't flow through the light bulb. And so it didn't matter which polarity it had, it just didn't light up. That's it. Too far, ABD, not part. Yeah, okay. Okay, so I'll let Christian start off with this slide.
Sure. All right, so we talked about a lot today. Talked a lot about electricity and circuits and all kinds of things, but we really want to make sure that, the things that we talk about today stick. So we're going to start off with this first question, thinking about what are some differences between conductors and insulators. You guys can go ahead and type that in the chat. And think back to what the different examples that we talked about for what an insulator and a conductor was. So we said conductors were metals, and insulators were like things like rubber or wood. Oh, I see an answer. Yeah, conductors let electricity flow. Insulators don't. They are opposites. Yeah. Okay. Good answers. Because the electrons are moving. Right. Great. So next question. Is how does polarity of our circuits affect our experiments? So think back to what we talked about. What does polarity mean? Polarity means, and then type your answer in the chat about what you think polarity. And you can also think back to the example of go-karts if that helps you a little bit. Plus minus. Okay. Yeah. So also think back to the circuits that we worked on, right? What happens when we flipped one of them and why? That has a lot to do with polarity. From negative to plus, right? Okay. All right. So if you guys remember, when we first introduced polarity, we introduced it as polarity is blank. If you remember, polarity is direction. So I want you guys to think about how does direction affect our circuit? If it helps to think about, maybe think about the lights that flipped. So when we flipped the light, electricity didn't move through it. So polarity is really important in our circuits. So if the direction is wrong, then electricity won't flow. So it's really important to keep track of those kinds of things. And if you guys kind of remember, we touched on it very briefly, talked a little bit about short circuiting, which is basically when the electricity isn't able to go through the light bulb because there's a kind of shortcut that the electrons can take where they don't have to. So next question, parallel circuits. We talked about are kind of like ladders, right? So for that, I'll let Aditi kind of explain it.
Thanks. So yeah, so if you remember and think back to the video we just had on parallel circuits, what happened when more lights were added? How did that affect the brightness? Were they as bright as each other, or were they less dim, or were they brighter for whatever strange reason? What do you guys think? Same brightness? Mm-hmm. Yeah. Yes, exactly. Yeah. So yeah, in parallel circuits, when we use LED lights, the brightness is the same. It doesn't affect the brightness in any way. Whereas in series circuits, like we saw, adding more lights to the circuit made it dimmer, made the brightness, it lowered the brightness. And so put together, what do these experiments tell us about how electrons move through a circuit? What do you guys think? And if it helps, you guys can think about the go-kart example as well. How would you guys summarize? How do you think electrons move through a circuit in general? It doesn't need to be too complicated. Has to be a closed loop, yeah. Mm-hmm. Any other ideas?
So one interesting thing to think about also is, so I've seen a lot of people say it has to be a closed loop. Um, and so one thing interesting to think about is when you turn on your light bulb in your house, with your light switch, think about what closed loop that's forming. So, it's going to have the wire that goes from your light switch to your light bulb, but let's take a minute to think together about what sort of closed loop is going to form with your light bulb in general. Where is this battery going to be? So one interesting thing to think about is the fact that you guys might have heard of things like power lines. And so one interesting thing is you can't just have one line sort of going straight to your light bulb. There still has to be this closed loop forming between your lights and the power plants, which is kind of an interesting thing to think about. So you can see that these closed loops are really important for all of our circuits, even the ones like your light bulbs or your lamps. All right, so that's it for the actual presentation part of this event. So what we're going to do now is we're going to open up the Q&A to just be questions that you had about this presentation involving circuits, maybe questions about science in general, what it's like to be a scientist, what it's like to go to college. Weird, I know, but yeah, what it's like to go to college. So if anyone has any questions about either circuits or electricity, science, being a scientist, being a student, we would love to answer your broader science questions as well. We're going to do this until about, let's say 5:50, 5:55, and then we're going to talk about the worksheet. So we'll give people a few minutes to sort of think of some questions. So yeah, if you can put all your questions in the Q&A feature, just so we can organize them. If you need help finding the Q&A feature, let us know and we'll guide you there on Zoom. It should just be on that bottom bar.
All right, so our first question is, what do you do? So I guess Charlie should start off with that.
So yeah, so what do I do? So I, as a 16th grader, have done a lot of science at this point in my day. Still have a lot of ways to go to still learn a lot of new things. That's one of the awesome things about science is that there's always new interesting things to learn. So what I do is I've actually worked in a lot of different types of science. So I've worked in things like experimental science. So I've done things like, actually use a wrench to tighten some vacuum chambers, which is just like basically a box that we just sort of suck all the air out of because the air might mess up our experiments. So I've worked with those. I've worked with programming. So I've had to code things on my computer, like trying to figure out certain things about physics. So things like a simulation. So I'm trying to sort of pretend like my computer is the experiment and figure out what's going to happen. I've sort of figured out like I've worked with the Large Hadron Collider doing some analysis for them. I've done some really interesting things there. If you guys have questions about the LHC or anything like that, would love to talk about that too. Yeah, and then right now I'm working on something called cosmology, which is just trying to figure out like how did the universe begin? So, you might have heard like the universe is like 13.8 billion years old. That's something that a cosmologist would wonder about. Like, how do we figure out how old the universe is? What stuff is in the universe? So this is things like dark matter and dark energy, if you've ever heard of those. And so I'm working on sort of cosmology right now.
And as a follow-up question, someone asked, why did you choose to be a scientist?
So Christian, do you want to maybe tack that one first?
Yeah. So I chose to be a scientist because when I was little, I always wanted to learn about really tough questions that a lot of people couldn't answer. You know, are there aliens? Where did the universe come from? You know, am I really, you know, am I really like, is time like, you know, does it work forwards and backwards? Is time travel possible? Like those kinds of questions. And science is the field where you get to answer those kinds of questions, right? You learn about a very specific thing that you find very interesting, and you get to start to do experiments and make theories and predictions about those kinds of things. So I was like, wow, if I can do that for a job and get paid while doing it, like that would be great. So I chose to be a scientist because I love answering and questions and learning about different things.
Yeah, and I don't mind answering that as well. So I chose to be a scientist because I actually started like I like maths. I think it's really logical, and not surprisingly, science is logical as well. In fact, maths was created in to support science, and so based off that, I started liking physics because I thought maths can be applied in physics, and so now here I am. Although I don't know what I want to do like specifically. So yeah.
Great. Cool. So I see we have another question here. So how is energy converted to electrons or electricity as we know it? So electricity is the movement of electrons, right? So as the electrons are moving, kind of like go-karts that are, you know, going down a racetrack, their speed is their energy. So by going fast, they have energy. So when we talk about electricity, we just mean a lot of fast moving electrons. And that's what electricity is. And that's where we get energy from.
So let's look at another question. So let's see. What if both conductor and insulator mix together? So how then would electricity work? So that's a really interesting question. So what if there was something that isn't quite a conductor and isn't quite an insulator? Um, so one reason why that's really interesting is because you might have heard of something called salt water. Oh, you might have heard of salt water. And so actually, I think someone mentioned in the chat, fresh water actually doesn't conduct electricity. So fresh water, when there's no salt in the water, likes to not conduct electricity. And it's when you add salt into the water that it actually conducts. So what you can see is the salt is actually the thing sort of conducting the electricity. And so the reason that's interesting is because, you know, you have something that's not a conductor, but you add a conductor and the overall thing becomes a conductor. There are also things where you might imagine it depends on how you mix them together. So, you know, you could have like a big piece of metal, but if you put a solid piece of rubber in between it, electricity isn't going to flow anymore because the electricity can't sort of get through the rubber. And so it's going to depend on both like how it's mixed together and what you're actually mixing together.
Okay, so we have another question in the chat, in the Q&A. How will vacuum suck all air and how? So basically what a vacuum is that it's empty space. So there's no air per se in a vacuum. And so there's something called a pressure difference, a pressure gradient force. And so air will move in to replace that empty space. And that's how vacuums suck all the air in. So yeah.
You can kind of think of it like a cup with water, right? If you pour water into a cup, it'll fill the space that is the cup, and air does the same thing with empty space. Cool. So let's see, we have another question. Who created technology? Well, technology isn't one specific thing that is created at one point. So technology is a lot of things. It's computers, it's machines, it's all kinds of really, really awesome, cool stuff, right? Even your phone is technology. So it's not necessarily been created at one point, but over time, technology has been getting better and better and better because people have been making more and more inventions. So inventions are part of technology. So there's no one person, but there are definitely some pretty important inventions like light bulbs or even how to use electricity, which was, those are all very important things. A telephone, the computer, very important inventions that are all part of technology. And again, if you guys have any more questions, feel free to put them in the Q&A.
Yeah, so if we have any questions about, the types of science that we've done, if you have questions about like with me, cosmology or astrophysics with Christian, or just general things in general. Do we have a vacuum room in our college? So the interesting thing about vacuums is you don't actually have like a full big room that's under vacuum, because it's really hard to sort of push all the air away. Because, if I'm just sitting down in my living room or whatever, the air likes to roughly just be everywhere. It likes to be over here, likes to be over there. And trying to tell the air to not be in this region is really hard. It requires a lot of energy to make the air not be in a certain place. So making a vacuum the size of a whole room is really hard to do. So what we do is we usually create like small boxes, which we then remove all the air from there. And the reason that's useful is because the small box is smaller than the big room. So it requires a lot less energy to make a vacuum of that size. Does that kind of answer your question? All right, cool. So I think what we're going to do now is we're going to talk about the, and we're going to keep answering questions as they come up in the Q&A. But another thing we're going to do is we're going to talk about the worksheet that we provided. So I'll send another link in the chat just in case someone missed or was not able to see the worksheet before. So we're going to work on this for just a few minutes. So if everyone could go to this link together, we could sort of work through this worksheet together. So I saw in the chat that some people did end up getting a bingo. Great job. We're glad you guys were able to follow along and see all the words and get all the bingo parts. So why don't we sort of take like 5 minutes, and if you haven't already, go through the word search, go through the worksheet, and if you have any questions about the worksheet, please feel free to ask in the chat. We'd love to try and answer your questions about the worksheet, because it really sort of cement your understanding of today's presentation. Well, we'll keep going through questions in the chat while we're sort of looking through the worksheet. So Christian, if you could share screen maybe and show the second page of the worksheet. We'll take like a few minutes to look through it.
Yes.
And don't look at the last page, because that's where we put all the answers, just in case.
Oh, okay, you got it. So just the second page?
Yeah, just the second page.
These are all the answers. There's the second page. Cool.
By the way, guys, someone has asked, how is NASA making microgravity rooms on Earth? Any ideas?
Microgravity rooms.
That's a good question.
That is a good question. Yeah.
What was the question? Sorry, I was looking at something else for a moment.
How is NASA making a microgravity room on Earth?
Oh, that's a good question. Yeah, I'm not quite sure what a microgravity room is, but I think I've heard of that before. So if you've ever heard of like a wind tunnel or something like that, basically what they do is they just have like a giant fan that you stand on. Well, it's underneath like a grate that you stand on, so you don't actually fall into the fan. But just like if you blow a fan at a balloon, the balloon gets pushed, right? And you can imagine like the balloon is basically having air be pushed on it, and so then the balloon is getting pushed that way as well. So what happens is if the fan points up, then the balloon would get pushed up. And if the fan is strong enough, even you will get pushed up. And so if you make the fan go a certain speed, it'll start pushing you up more and more because like if a fan isn't moving, it doesn't push the balloon. If it's spinning really fast, it pushes the balloon a lot. And so the idea there is that if the fan is going fast enough, it'll not only push a balloon up, it'll push you up. And if you push up the same amount that gravity pushes you down, it's sort of like nothing's pushing on you at all. So that's how NASA might make like a zero gravity environment in that sense. Another way is that they just put you in a pool of water, because if you're in water, you just sort of sit there. But if you were just standing above the air, you would fall down. And so being underwater is close to being like in zero gravity, because the water pushes you up more than gravity pushes you down.
And we have a final question here. Who created a vacuum? So a vacuum wasn't really created by someone, as far as I know. It's just that space is naturally occurring vacuum because there's no kind of air or atmosphere in space. So yeah, no one created a vacuum.
The first person to invent something that could hold a vacuum, where like they had their own little box that has a vacuum in it, was I think John Ambrose Fleming, who was a scientist in the early 1900s. He did it for chemistry. So again, yeah, vacuums exist all the time because they exist in space. But in terms of here on Earth, the first time it was ever achieved by someone was in the early 1900s, which is about 100 years ago. So quite a while.
I see another question in the chat. Who is your favorite physics scientist? Yeah, why don't I don't know, Christian Aditi, do you have a favorite scientist? I know mine, but I want to hear what you guys have to say first. We have time for like one or two more questions before we have to wrap up.
Favorite physics scientist? Oh, that's a good question.
Yeah, I think mine is probably Emmy Noether. So she was a really awesome scientist back in the day. I think it's really kind of cool because Albert Einstein was, he just invented general relativity, which basically tells you how gravity works in situations where sort of Isaac Newton's idea of gravity doesn't quite work anymore. Einstein sort of came up with a better description of gravity. And he was really struggling with this one problem with general relativity, and that was like there's this one really big idea in physics, and that's that energy is always conserved. So the idea was like, I might like, my watch maybe right here, it isn't moving, and then suddenly I drop it and it's moving a lot, and so it has more energy. Well, the reason is because it had gravitational potential energy or something like that. And the point is, in normal physics, like energy is always conserved. Like the amount of kinetic energy I gain is the same amount of potential energy that I've lost. So the total energy is the same. But in general relativity, it just seemed like this wasn't true anymore. And it took Emmy Noether to sort of come up with the reasoning of why that isn't true anymore. And in particular, she was able to sort of figure it out in a really awesome and general way. And she came up with maybe one of the most important theorems of physics, in my opinion, called Noether's theorem, named after her. So that's why she is my favorite. Also, women in science are always really awesome. So they always do really cool things. So empowerment.
I can go next about mine. So, there's a lot of great physicists and a lot of great scientists. I would say probably my favorite is Neil deGrasse Tyson, because he works in astronomy like I do, and he's also like super smart and just super funny. And it's always nice to see somebody, you know, who's kind of a darker skin color working in science, because that always gives me hope that one day I can hopefully be on national television just like him. But yeah, I think the work that he does is really important, and he has the way he explains science is just super awesome, and makes even really hard things sound really easy.
All right, we're sort of wrapping up. So we have only 2 minutes left. So we have time for like one or two more questions. We have time for one or two more questions, maybe just one more. But if there are no more questions, and it could be questions about us or about the worksheet, but yeah, I think we're almost out of time. So we're probably gonna wrap up now. So thank you guys so much for attending. We hope you learned a lot. We hope you got to ask the questions you had. Yeah, and with that, we really enjoyed having you guys. So thank you so much. Christian, do you wanna maybe stop sharing for a sec so we can do the outro slide? Cool. Yeah, we're so glad to have you guys, and we we hope you've had a great time at the Bay Area Science Fest. Yeah, we hope you get to go to some of the other super awesome events that the festival has organized. They've done a really awesome job sort of making all this stuff happen online, you know, given this new normal and all that good stuff. Yeah, we're really happy to have you guys, and I guess we'll hopefully see you around. And if you ever have, um, yeah, we hope you stick with science because it's really cool, and I guess we'll hopefully see you around one day.